S&P video conference for September 2019. And today we're going to talk a little bit about a number of issues that fundamentally impact complexity reduction, a rapid address different types of
Joe, you cut out for a moment or two there. Also, Janet's online. I don't know whether you've had her join the thing yet.
yeah, Janet.
Yeah, I can see it. So
okay, good.
But
yeah,
I did lose the audio for a minute.
Do we have the audio now?
Yes.
Okay, good.
Yes.
So with that, I'm going to go ahead and move on to the next particular overview part here. Let's look at this one, I think is it. Okay, so this is the overview I sent out earlier, and in this session we're going to review the logical properties described in three general areas. And I've been looking at the animated logical graph concepts from Aubrey. Kind of stopped doing that in the middle of the summer, and I have some more time to get back and look at that. And kind of the points where we stopped there, we're looking at the idea of equivalence and distinction, and also the ideas of an arithmetic and operators that go with logical operations. So this also then, when looking at animated logical graph concepts, then reminded me of some of the work that was done by Combs in his method for rapid inference, and which also connects to the augmented model exchange isomorphism. It also connects to the augmented Boolean operators that were created by Warfield. So just kind of as a little bit of a review on the list, when we were Aubrey's animated logical graphs on the system science list he's talking about the operations of equivalence and the operations of distinction. And so the logical properties that are associated with equivalence, or the relationship of equivalence, of course, is reflexive, symmetric, and transitive. And this gives us a direct connection to the AMEI and to Warfield's logical operators. And then given the relationship of distinction, the logical properties are irreflexive, symmetric, and transitive. So these fundamental operators and fundamental logical properties are only different in the fact that they're either reflexive or irreflexive, which is kind of interesting because it's important that just the two basic operations of making a distinction and inquiry that are only different by one logical property. So that is a kind of an interesting point. I'll just leave it at that. So then the additional materials of the Combs fuzzy logic and the Combs rapid inference. I'm going to send out that link. And then, of course, send out a link to our paper on foundational aspects of system complexity reduction, and then the augmented model exchange isomorphism. So next, I'm going to just kind of walk through some of the highlights of Combs' work, which I think are interesting, and kind of start developing a little bit more of an argument about what we can, how we might be able to use these features in a little different way. So Bill Combs worked at the Boeing company. He worked in their computing area. And one of the areas he worked in was the idea of real-time control, working with incomplete data sets, working with a number of very difficult type of computational problems and contexts. And when he was working with fuzzy logic and looking at inference systems and rule sets, he, like many other people, came across this problem of the explosion of rules. And the explosion of rules basically comes from the fact that there's a lot of uncertainty. And so Bill decided that, no one was looking at the fundamental reason for this explosion in the rules. And so he went through and developed what he called the union rule configuration for fuzzy rules. And he gives the mathematics in his paper. But basically what happens is you take each specific relationship, the antecedent and the consequence, and you put them together so that you don't combine all of the different logical relationships together in one large set. You just do them one at a time, and then you need a different way to integrate those, or to create an integrator or an accumulator for those. So as as Bill points out, they're working with propositional logic constructs. If P and Q, then R. And the primary thing is P and Q. You have to know them both. And as you have more and more antecedents, more and more variables, then you have to know each one. So if you don't have them all, that doesn't really work. And what do you call this? The intersection value. So it's the intersection value of any number of antecedent elements. So you have to have them all, and they have to be available to make a calculation on whether it's true or false. And so he calls that the intersection rule configuration. As he points out, that there's two significant difficulties with the intersection rule configuration. So the P or Q changes, W is altered as well, producing different relations in R. So they're tightly bound with each other. And W's relation with R is only accurate in our ability to find P's intersection with Q, so that we don't have a relationship with P is not directly related to R, and Q is not directly related to R. It's the intersection, it's both of them. So to have an operation, and then that has a relationship with R. Bill goes through and performs some calculations and comes up with a truth value equivalent relationship, but where we have we have a direct relationship between P and R and Q and R, and remove the and connector. So what this does is allows you to have a direct relationship between the antecedent and the outcome. So what he's done here is he's gone through and he's done the truth tables to show that when P then R, so if we do P, we have the antecedent P, then we have the resultant or R, or Q then R. So in this case, P and Q have been separated from each other. So we now have a direct relationship between P and R and Q then R, which are put together by the OR operator. He shows that basically these truth tables are the same. And when you walk through that, the upshot is that you are able to actually make a determination on very specific pieces of information as they stand by themselves. So they're not all dependent on each other. So the uncertainty goes down. Because and here is the formal transformation steps for the propositional logic that he put together to show that the initial intersection rule configuration, P and Q then R. And he goes through the mathematics, and then P then R, Q then R, connected by OR, by the union rule combination. So the connection here is the difference between the OR operator. Started looking at the difference between the OR operator and the AND operator. When in Warfield's work with Boolean algebra, the AND and OR operators are represented by regular arithmetic operators, plus and multiply. So these operations then are different, and the operations and for the outcome are quite different, and there is not a direct connection between all the antecedents. They're now basically separated. And if one is, say, for example, if one of these is true, giving the OR composition, right, then the statement is true. That would not necessarily be the case in an AND configuration, because you'd have to know both. So there's a number of advantages to the union rule configuration, which has a connection back. If you look at Warfield's Boolean arithmetic, has a connection, and then I believe that has a connection back to the arithmetic that John Aubrey's talking about. So, this is kind of high-level hand-waving right now, but I wanted to take the time and kind of discuss and point out these different areas and how they may be related, and the benefits of looking at Combs' work is that he specifically talks about the combinatorial problem, and it's not just unique to fuzzy logic, it's unique to all logic type of formats. I mean, it applies to different types of logic. And Bill Combs gives a number of examples, a number of concrete examples. So really the goal here is to see if we can take the concrete examples that were put together by Bill Combs using the transforms and the arithmetic of Boolean logic developed by Warfield, and see if we can map it back to the work that the animated logic graphs that are part of John Aubrey's work. So that's kind of the main idea here, to identify these concrete examples, use a specific type of Boolean arithmetic and operators, and then see if we can map those back to the more abstract work that Aubrey's doing. Okay, so we've gone through this, and another specific part about Combs' work, of course, is that he then, once he's put together this URC approach, creates and makes an argument for the fact that you can go through and make your judgments, your evaluations. They don't necessarily have to be continuous in the fuzzy logic domain. You can make them singletons. So in this case here, he's gone through and he's done these rule sets. There's been a direct connection between them. He reduces the rules. A very simple example here of how to map these across. But when we're looking at this part, we're looking at what we're mapping to. It's important to note that in this particular idea of the premium, it goes from low to high, which is a value judgment. One is greater, and it has a scale from 0 to 1, so that it's ordinal, and one is less than the other. And so we're now taking, in this particular case, we're taking propositional logic out of the nominal scale, which is just true or false, putting them into the ordinal scale, which has a range, is continuous. And the part of work that Warfield did when he added greater than or less than operators to the Boolean algebra, I believe will also translate into these areas. But this is an example where Bill was using continuous values in fuzzy logic, but then he goes through a little later on and shows an example of how to do it with a cumulator. Here we go, where you just have singleton values. So you can, one of the advantages of this approach, by separating the antecedents and giving each antecedent a direct connection to the consequent, and having a scale, allows you to create these singleton or specific discrete values and then accumulate them over a set of rules. So as we walk through those and look at those, here's the accumulator. Okay, so here's our inference engine diagram and the URM inference engine. So there were issues with the integration operators, and when fuzzy logic first came out, Bill talks about the different types of integrating functions here. And in the past, I've done simple accumulators and even different types of inference engine approaches, so that this particular idea of an inference engine, or the integration of these specific values, is still kind of open for development, for application in for certain specific types of problem sets. Okay. And it says right here, this is really important. It says that QRC is not limited to the streamlined process. You can use any fuzzy logic functions because fuzzy logic is able to work with any valid rule configuration. But I believe some of these logical configurations and the idea that you can change from a specific discrete value to a continuous variable is also applicable in other predicate and propositional areas. And I think that's one of the things that Warfield was looking at. I think it's one of the things that within their triangle and their cube that Aubrey looks at. Now, I haven't quite been able to put together some good examples yet, but the goal, one of the goals would be to be able to take Aubrey's work and create or even reproduce this type of insurance problem or certain rule sets that we could translate back and forth between them to see if that's possible. So that's a lot of really compact ideas real quick. Are there any questions?
No questions. I think this is very interesting, and I can see where you're going. I like the fact that you can see that he's dealing with a real situation where you have different levels of confidence in your data and your rules and the way the rules combine. And so rather than making an assumption about the rules or the data and being sort of boxed into a corner, you can get the best use out of what you have in a real situation. I think that's a common theme here and in Warfield's work, and I guess it's come up when we've talked to Kevin about where do the relations come from? You know, they come from some group, and to what extent do you go from there saying that these relations are fixed because the group has said that they are at some point in their judgment, whereas one should always have also a sense that maybe the rules aren't fixed and maybe the rules will be changing as you go along. Anyway, I appreciate what you're doing here. I can see how it would be really good to bring them together.
It's that's well, the point about the rules changing is very important. It's of course, obviously you have to work with a static set first, but you're right, you can, because you have now separated each specific antecedent from the consequent, then when you don't get information about one specific antecedent, if you have rules about that, they don't fire. It doesn't matter because they are not tightly bound to that specific rule set. I think the other important problem is, and his issue is actually when you have maybe sub-rule sets, things that are patterns you see within the data that are don't include all of the antecedents, but just subsets or sub collections of the antecedents, and they behave differently, and they may then themselves generate either a new object, collapse it into an abstraction, or it may have a different type of impact. So those are just generally things that I think that are really important and really kind of interesting with this kind of inference engine. And it's Build has, it did some work in with electrical engineering folks on power grid optimization, and they've done specific real-time control. So there are examples of this work out there. There's, as far as I know, there's no open source union rule inference engine. Everybody kind of keeps that closely held, but as I said before, I wrote one or two fairly simple ones, and that would be another way that you could actually start looking at how these things compare. The idea about separating the antecedent from the consequent and allowing you to look at different levels of abstraction kind of indicates that there's a possibility that you could have a digraph of these subcomponents, and the subcomponents will be partially ordered within the larger set. And then depending upon how that specific pattern fit, you could have different rules fire. I talked to Bill about that a little bit when we were working on this, and it was something that he never really got the time and resources to work on. But what they did do is, like, at that particular time, they were working on large volumes of breast cancer data from many, many different sources. And the data was really ugly. It was in different formats. It wasn't clean. It had different characteristics. And I think that this specific union rule inference engine, the first application they did on that, I believe, was on that breast cancer data set. Because what they could do is they could go through in this massive amount of data and they could filter it for the antecedent and the consequence at some value factor, and then do an integration. So if there were antecedents that were missing, it didn't matter. So that makes it very adaptable and flexible. So it's a pretty interesting approach.
Mm-hmm. Mm-hmm. Are you familiar with people using this in Bayesian belief net systems? Some of it sounds similar, and it sounds like it would be something that could be leveraged there.
Well, the Bayesian belief nets, I think that, you have from my understanding, you have two basic contexts. First context for the Bayesian belief net is you need to come up with your antecedents, your prior probabilities, right? Those have to come from somewhere. So there's the activity of getting your prior probabilities. And then once you have your prior probabilities, then you apply them, okay? So I would think that this specific URC would be very applicable in developing the prior probabilities. Mm-hmm. The application of the Bayesian belief nets, once you have your prior probabilities, is fairly well-known and straightforward type of approach. But there is the problem of missing information.
Right.
And so the missing information and the coupling, and Janet, that's really a good question. Now the kind of things in my head that, okay, could you actually decompose the Bayesian logic into a union rule because it is a intersection rule, isn't it? Okay, so yeah, well, something else.
Something else to throw into the mix. Yeah. Okay. Well, let's move ahead with the rest of your work there.
Yeah. So anyway, so that's basically what it is for that. And so then let's see, what else did we have we were going to work with today? Let me stop this screen and go and look at no, that's the wrong one. So let me just go back here and make sure that looking for here we go. I've got to come up with the document somehow. Okay. Well, all right. So this is the structural modeling framework that that was mentioned in the was mentioned in the note. And what we talked about here, of course, is complexity reduction and complexity management. And we brought in Warfield's work. We also brought in Combs' work into this one. The idea here is that uncertainty is reduced when you reduce uncertainty, you reduce complexity, computational complexity and cognitive complexity. When you increase uncertainty, the reverse happens. You increase complexity. So the key of being able to take a specific antecedent and disconnect it from all the other antecedents and look at it by itself and have the information you have about it, right, is important. And the integration, the value set integration that you use to look at a number of these antecedents and how they relate to the consequent can change based on those specific antecedents are available and in play. So this is our basic structural modeling approach. And of course, we're working with the structural integration modeling piece. And the structural integration modeling is the type of integration you would use in URC is, again, another mechanical example of how you take information, encode it formally, and then apply that to your work. So, in detailing the operational aspects of basic structural modeling, this is essentially in the mathematics component. In Combs' work, this is basic mathematics. He's pointed out a different way of using the logic than the more common way. And with the union combination rule, URC union rule combination, that basically then is over in our mathematics area, in the formal mathematics. interpretive structural modeling, the specific logical, empirical, conceptual properties right here. So those would be in the value sets within the application in the integrator. So if we looked at, let's say, for example, in the insurance, the specific empirical conceptual properties, what is low, what is high, how does this model relate to the real world risk, then that is basic, that data and those rules, the consequence are here, come from the real world. And putting them together in a set, of course, is in the interpretive structural integrative modeling area. So the Boolean algebra, that augmented Boolean algebra from Moorfield, he added the less than operator, the greater than operator, less than or equal to, greater than or equal to, and Boolean subtraction. So, and then of course there was matrix subtraction and matrix ordering that are available because Moorfield added these concepts. So these concepts then within the range of a continuous value set allow us to address the same types of context that you would use in fuzzy logic, or that you would use in real world value determination. And using the idea of a singleton in fuzzy logic, then you can translate back and forth between the Boolean singleton values and a continuous range on a scale once you have these operators that allow you to actually do that, so that you come out of the nominal true false and you step up to the ordinal where you have, oh, okay, this is greater than, less than, we have an order, we have a scale, and we also have true false. So these are things that kind of, I believe, can be put together in a way that's beneficial. And then, of course, the directed graphs and the pros and the AMEI. These are areas where there's a possibility, I'm not quite sure yet, but I think there's a possibility that you could group the certain antecedents in a collection into different groups, and then those different groups of antecedents could be related to each other given the directed graph. The directed graph itself would represent the logic, and then you would have partially ordered sets within each one of the nodes. I think that would help quite a bit, but I haven't done any coding or calculations in that area yet. It's just more or less come to mind in the last week or so when I've been trying to pull these major areas together. Okay. So in the work we've done to this point with the augmented Boolean algebra, what we've done is use this observation that we have our decimal operators here and we have our Boolean operations here. We just notice that they're the same except for this. And in decimal operations, 1 point plus 1 equals 2. And of course, the Boolean operations, it's 1 plus 1 equals 1. But besides that, everything else is the same. So instead of going through and writing a set of mathematical operators and matrix operators to address the augmented Boolean operations, came up with an approach that just uses decimal operations, but any number that's greater than 1 is then assigned back to 1. And that works, so that it really saves a lot of time and a lot of effort in writing a new approach. And you can also then use things like Sage Math Tool. You can use all the mathematical systems out there that are available and been tested by mathematicians for a long time. You can use them in the decimal mode and then just do a filter transform to come up with the augmented Boolean output. So this was, of course, the initial cities problem that we talked about before. And I've gone through that quite a bit. The thing that really, the key characteristic that made this work was that the relationship here north of was, and the relationship was an order. It was a, one is greater than the other, and there was a strict order, so that the fundamental mathematics that came out of the interpretive structural modeling works very well. If you have a strict order, if you have a partial order, it doesn't work as well. And structuring relationships like impact and so forth are essentially based on non-strict order types of relationships. So with that, I'm just going to emphasize the fact that starting with John Aubrey's work, looking for concrete examples, taking a route through the Boolean operators of Warfield, and then looking at the URC approach from Combs. We're going to try to focus on making some direct connections and provide some concrete examples of the animated logical graphs. And it's might not get it done, but this is kind of the general overview of what our goal is. And I thought I would take the time to talk about it today, just so that I could get some early feedback, and also to see if there's any other areas that are connections or things that people would like to think would be important to show, to also integrate into this process. Mm-hmm. So with that, again, I'm going to open it up for questions, comments, and discussion.
Is it possible to get John to do a presentation to us on the animated logical graphs?
I think the best way to do that is to ask him. So I'll do that.
Great.
It's I have. Well, I've one of the characteristics of John's work is that it's voluminous.
Yes.
And
right. Yeah, it's unfortunate. That's sort of deters sampling because you're not sure where to go. Yeah.
And so one of the things that I've been trying to do is find some foundational piece that I could focus on and then go from the abstract to the concrete and see if I can start making that connection, because the all of the abstract concepts that he presents, I believe, are very valuable, but I think they'll be much more valuable if they were available to be used. And so that's kind of my view of it. And it's the cactus graphs that he has I think are great because they show the structure of the steps and the preceding type of context and the outcomes. So that's really, I think, a very powerful graphic technique.
Mm-hmm.
But I'll make a note to ask him if he would do that.
Mm-hmm. Very good. Yeah, at a minimum, having concrete examples is very valuable for getting toward usability. But I've been aware of his work for, I guess, decades, but always sort of admired from afar because I didn't know which foundational element to latch onto and get oriented. So it'd be great to have him available to give his view and then answer questions from us.
Good. I'll see if I can arrange that. See if he'd be willing to do that, or if he could give us some pointers to some more specific information.
Mm-hmm. Right. Yeah, I guess. Yeah. Does he on his site have a learning path through his work? I guess don't want to burden him with that right now, but that's something that would help future generations confronted with his the body of work there.
Yeah, I'm not sure. I think one of the key things that I finally picked up on his work was the idea where he's talking about Peirce and the logical variables. And so the logical variables and how these logical variables fit into a logical algebra. So
Mm-hmm.
if we look at the constricted set of logical operators, then the augmented Warfield augmented Boolean algebra, and then we look at the applications from Combs' work, then to me it seems that there's a way that you can talk about the logical variables, and you can also talk about the logical algebra. So the algebra comes from Warfield's work. The variables would come from Combs' work, because he allows you to make direct connections, to separate everything into variables. So, so we'll see. That's what kind of drove me down this path. It might be a dead end, but we'll.
Oh no, that there is very good. So the algebra comes from Warfield's work. The variables come from Combs' work, and then from John's work. How would you put that in the same sentence?
Oh, well, what John appears to be doing is exploring the ability, or exploring the idea of logical equations and logical variables and logical operators.
Mm-hmm.
So from from Peirce's work, I think what he said was that he spent a couple of years in libraries reading Peirce's work to try to figure out what those operators meant, right?
Mm-hmm.
And so the operators, when he was talking about De Morgan's law, right? And how those equivalents worked in that algebra, when I read that, I immediately thought about the work that Bill Combs did in the URC.
Mm-hmm.
And so it is not, Bill took it from the idea of being an intersection and having everything combined, the AND operator, and he transformed it into the OR operator. So now we have two. So here we're working with operator variables, right? Still have the same truth table, but we have operator variables. Now, what is the impact of that? So the impact of changing from the AND operator to the OR operator is tremendous complexity reduction.
Mm-hmm.
And also, it allows you to either switch between a continuous type of value structure or a discrete type of value structure. You can either use that as switches, yes, no, or you can use it as a continuous variable like, oh, this is better than that, this is really good, this is really bad. Things that are more continuous kind of variables in value. And so that approach then allows us to engage it in the empirical realm of getting those values from real world engineering.
Mm-hmm. So maybe one could say in a elevator pitch or short form rough that Warfield, if they all deal with logic, algebra, and variables, Warfield emphasizes the algebra path, Combs the variables, and Aubrey the logic.
Okay, yeah, they all Aubrey the dynamic logic.
Okay, that's good.
That's the idea about the variables. Variables
Right.
allow you to have dynamic equations.
Right.
Right. So you can take one equation, you apply it to all these different things, right? So yeah.
Right.
So the dynamic logic of Aubrey, exploring that through, right? Looking at the Warfield algebra, Warfield augmented Boolean algebra, and the Combs basic operations, the logical operations, the URC.
Right. What Combs brings for the variable clarification. So you asked what else might be brought in here. I think this would be further down the road because I think bringing these three together would be really good. But George Friedman's work with the bimatrix approach.
Bipartite graph.
Yes, right.
Yeah. So
yeah.
Did you read the paper that Mary and I wrote on that?
No, I don't think so. I think I missed that.
I'll send that out. So we made a connection between Warfield's work and George's work, and to show how specifically that in at least in the introductory type of approach can be greatly simplified. So I will send that out in the notes for this one. And so there's some issues there fundamentally that we talk about in that paper with George's work that would make it I think difficult to integrate it totally, but through the view of Warfield's relations, then I think you can achieve a lot, or maybe even all of what George's approach is, using the process that we outline in this paper.
Mhm. Is it the case, and I didn't get very far in George's book either. That's another thing on the long list of things that are partially done. Is it the case that the main the foundational difference between Warfield's approach and George's approach is that Warfield uses the n-squared type matrix where a set of objects is related to the same set of objects. So so the rows and columns are of the same type. Whereas in the bipartite graph, you have a matrix where the rows and columns are of different types.
Well, there's a number of issues. So actually, George seems to use two types of graphs. We kind of combine those into a more of an n-squared type of approach.
Mhm.
More fundamentally, however, though, is that he allows sets to have duplicate elements.
Mhm, mhm.
And so when you have the multi-set component, then we now are looking at a different, almost a derivative level of interaction and relationship.
Mhm.
And so again, we talk about this in the paper,
Okay.
and we've suggested 2 or 3 different ways to kind of look at it. But yeah, it's and it is thick. It's very thick, but
So that would be a for future elaboration. It seems like allowing that would be part of making the as Coombs was trying to do, making a more robust system that could handle real data and rule combinations that were, as you were saying, with the messy data with breast cancer. And this reminds me of my work with trying to help people make sense out of their research projects and all of the ways that one can have messes. So the duplication would be one, allowing duplication would be one direction one would want to support ultimately as part of the process of getting where you want to go. Anyway, so that's for future down the line. But yes, I'd appreciate the paper.
Okay, so we're getting close to the end of the hour here. Let's get ready to end the broadcast. I will send out a copy of our comments on the constraint theory, and that may be a good topic for next month. Or we'll see if let's see if any. Kevin was going to be online, but I didn't see him. So
very briefly, on September 2nd, John Aubrey sent out a note in response to Alexander related to a specific, or at least as specific as John Aubrey can at this time be, related to examples from a semiotic perspective that were written with he and his wife, Susan, I think in early 2000.
Great.
Okay, well, we'll wrap this up for today, and I'll send out the paper, and we'll arrange the meetings later on.
Very good. Bye-bye.
Thank you.